Hmm. Hi, folks. Welcome to chapter 9 on the measurement of uh, quality control parameters in high voltage equipment in dielectrics. This is lecture number 3 in this chapter, and overall, this is 37th of our lecture. Not many lectures are left anymore. Yesterday, we introduced in the last lecture, that is in the chapter 9, uh, second lecture, I introduced you with a very important, very sophisticated and very good revealing parameter, provides revealing parameters about the quality of the dielectric. The sharing bridge. It's a bridge, as usual, you might have learned number of bridge circuitries, and you have to produce a balance and null of the four arms of the bridge, and then you can measure the tan delta, and from there you can also infer, for example, insulation resistance, and if you have the value of standard capacitor with um, air or vacuum as a dielectric, you can uh, also, or the value of standard capacitor with which you are measuring, for example, the parameters of transformer oil. So there is a provision of standard guard ring capacitor. If you know the value of that capacitor, standard capacitor with vacuum or air as dielectric, then you can also calculate, determine from the readings the relative permittivity of the oils. So this sharing bridge was developed, as you know, in as early as 1919, as more than 100 years old, and very widely used in all good high voltage laboratories. So this was the derivation about the relative permittivity, the insulation resistance, and tan delta. How you measure, we have discussed that in the last lecture. So let's talk today about, as I just mentioned, about a standard guard ring capacitor for measuring tan delta of liquid dielectrics. So this has been uh, developed by many countries, and the sketch and a photograph of actual capacitor or instrument, you can say this is a basically an instrument. I'll tell you the important parts of this instrument, which has been developed by VDE. The This is a German specification, German standards, VDE 0370. So this is a standard apparatus known as test cell. How you can call it test cell, or especially designed according to VDE 0370 specifications in Germany for measuring dielectric properties of liquid dielectrics. And this is, as you see, is the overall view of the capacitor, uh, or standard capacitor, guard ring capacitor, you call it. Well, and actually the dielectric, that is the liquid dielectric, form forms a standard, in its standard form, a standard capacitor, and that looks like to be like this standard capacitor. The oil test cell. As you can see the photograph, B is the cross-sectional sketch of a standard guard ring capacitor as per VDE specifications. This is courtesy Halfley, Germany. We did purchase from Halfley because this is a very sophisticated instrument and very good instrument. As you see here in the figure B, the inner part is moving, means I mean to say it's solid. This inner part is solid, and when it is put inside the cell, as you see on the top, it fits in such a position that it forms a 2 millimeter, as you see, 2 millimeter thickness layer of liquid dielectric. The outer electrode, what you see here, this one, the outer electrode is actually fixed inside the cell, and the inner electrode can be taken out. And when it is put in its position, it forms a 2 millimeter thick film of the dielectric as shown by hatched portion. So this in this form, when mm, when the capacitance is formed, it is nearly a uniform field capacitor. It is weakly non-uniform actually. The eta, when you if you calculate for this this configuration of the two electrodes between which the capacitance is formed, it may not come out to be 1, but very close to 1, that is weakly non-uniform field. The guard ring, that means there is a separation of the portion under measurement and away from there. That, as I circled, that is the guard ring provided in this cell, and that takes care of the stray capacitances formed when you are measuring, because the stray capacitances formed may disturb your or may affect your measurements. And this is number 3, as you can see it here. This here, no, not number 3. This is number 6, as you can see here. This is guard electrode, as I mentioned. That is a circular. Obviously, the whole thing is circular. In the two dimension figure, the cross section is being shown. The whole thing, as you see from the top, is of circular form, and the high voltage electrode. Where is the high voltage electrode? Can you locate here the high voltage electrode? The high voltage electrode is 1 here. That means the outer one, the outer electrode of the capacitor formed by the dielectric is the high voltage electrode. And obviously the inner electrode is for the measurement. As you see, the inner electrode, that is number 2, is used here for measurement. One is also shown here, 1, and this is the inner electrode 2, the given shape. Now, the best part in it is that you can apply a varying voltage between the two electrodes, forming the capacitance or the capacitor of the capacitor up to 2 kV. That means at variable voltage you can make the measurement. Then the interesting part is that you can also change the there is a provision for heating the oil, and you can change the temperature of the oil. When you change the temperature of the oil, you know the tan delta changes, the relative permittivity changes. So you may like to measure the parameters of the oil at different voltage uh, or different field intensity applied between the electrode, because you can convert it into kV per millimeter, because it is a uniform field, and so the gap distance is of 2. The uh, no load capacitance, that is what I was talking about, is 60 picofarad. What do you mean by no load capacitor? It has been termed as no load. Actually, when you fill the gap between the two electrodes, not by any oil, but instead you leave it with air, or you produce a vacuum. So you can say the C naught, what we talked in the last lecture, the C naught, as you see here, this is C naught. That is the capacitance of the standard capacitor with vacuum or gas as a dielectric. So that is 60 picofarad. So and the variation in voltage is permissible up to uh, 2 kV. Amount of liquid required is only 40 milliliter, as you can see, is only about 40 milliliter of test sample is required, and the dimensions are 240 millimeter by 220 millimeter high. So the diameter is 240 millimeter. That means the diameter of the electrode forming the capacitance is 24 uh, uh, 24 centimeters. It's this big here, and the height is 22 centimeters, and the total weight is 10 kg. So this is the construction of the guard ring capacitor, a standard capacitor, and through this a standard method of determining the electrical parameters of insulating oils is made and are required to be measured. The specifications may require to measure it at a particular voltage, at a particular temperature, and if you want to do some further work, you can change the voltage, you can change the temperature. So this is how the tan delta, insulation resistance, as well as relative permittivity of liquid dielectrics can be measured. So that tells the quality of the dielectric. There are specified values. If the measured values differ from there, you that puts an alarm that you must do with the oil something to improve its quality. Yeah, uh, one can also measure the insulation resistance directly by a by an instrument known as mega ohm meter, as you can see here, known as mega ohm meter. So this instrument also we have in our lab. You can imagine the insulation resistance is actually the DC resistance of the or caused by the DC resistance of the insulating material. So DC resistance, RDC, uh, or you can say R insulation, offered by insulation of any gadget can also be measured directly with the help of a measuring instrument known as a mega ohm meter. So in case of solid dielectric, you can measure the DC resistance between the high voltage electrode, uh, which is actually at open circuit conditions, and the ground. So, but in case of liquid dielectrics, you may require the same test cell or standard capacitor as we just now described here. And that is being shown again here, the standard capacitor for the measurement of insulation resistance of liquid dielectrics is being utilized here. Yeah. So when you have the DC insulation resistance RDC and the specific insulation resistance of a dielectric are related in this fashion, as you can see it here. RDC is equal to rho insulation D by A, and with this you can write rho insulation is equal to you I mean for D by A you D by A, so you can say uh, rho, I can write it, rho insulation is equal to RDC A by D, and then you numerator and denominator both you put epsilon naught and a a epsilon naught a by d. This forms the capacitance C naught. That if you for instead of oil, when you fill the standard capacitor with air, considering relative permittivity to be epsilon r to be 1, so this this forms C naught. So this is equal to R dc C naught by epsilon naught. Unit C naught by epsilon naught, and that is what has been done here. So you can get, when the values are put for C naught, which just now we learned in that standard capacitor is 60 picofarad. The did we not? Is 60 picofarad, as you can see. No load capacitance, what we C naught is 60 picofarad, as you see it here. So when you put the values of C naught to be 60 picofarad, epsilon r is equal to 8.854 into 10 to the power minus 12 farads per meter. So we put the values, so you get the specific insulation resistance to be of the order of R insulation into 60 by 8.854 ohm meters. So this is how, yeah, the only thing here to precaution is to be taken. This is the instrument. This is the instrument, mega ohm meter, and is measuring, and this is the DC voltage is being applied. DC voltage is being applied here, and on the test object, when you can choose the voltage on the test object. It works actually. Should be written here. It works up to 1000 volts. This instrument works up to 1000 volts. It's not written here. I mean, you can choose the application of the voltage on the dielectric, and which is variable up to 1000 volts you can choose. U is the measuring voltage, and when you apply the voltage, the DC resistance to stabilize even the measurement because of the polarization. It stabilizes. So you have to give, as recommended by the instrument, a few seconds to be able to measure the RDC directly. You can measure the RDC directly with this instrument. Measuring cell, R here is the measuring cell. That means when you are measuring the insulation resistance of the insulating oil or transformer oil, and there is a G galvanometer or transformer with guard electrode you can put there, and the instrument would measure directly the RDC in mega ohm, and that works out to be thousands of mega ohm. The RDC works out the order of thousands of mega ohm. That means stabilized DC resistance of a dielectric is of the order of thousands of mega ohm. So this is another important resistance instrument. Insulation resistance also gets adversely affected with the bad condition of the dielectric. The worst of all would be the moisture content in the dielectric, or humidity, or even the quality of the dielectric would affect the value of the insulation resistance. So insulation resistance at different conditions of manufacture, after manufacture, are also measured as a parameter for quality control of dielectrics. So this was next, and now we will go to one of the very important uh, measurement, as you can read it here, the partial breakdown measurement technique in dielectric. We have discussed this when we were talking about the solid dielectrics, and in fact when we have talked about uh, gaseous, solid and liquid, in all the dielectrics partial breakdown takes place. In air, the partial breakdown is known as corona, and in solid, whenever partial breakdown takes place, it may cause a kind of a permanent damage to the solid dielectrics. And the partial breakdown activity is also there in liquid dielectrics. But since in the case of liquid dielectrics, as in the case of gaseous dielectrics, the dielectric mm, may get replaced near the electrode where the partial breakdown is taking place. That means at the maximum field intensity in the electrode system. So the significance of partial breakdown measurement in gaseous as well as in liquid dielectrics is also done, but it is not that damaging as in the case of solid dielectrics. So the partial breakdown in solid dielectrics are most damaging, as you read the first line of this uh, slide, and these may reduce the life of the equipment drastically. The damage not only depends upon the intensity of partial breakdown, but also upon the duration and location of the partial breakdown. At which location the partial breakdown is taking place. If the partial breakdown is taking place at the ground electrode, it may not be that damaging as when it is taking place at the high voltage electrode where the maximum field intensity is there. So, and the time required for the, that is duration for the formation of conducting path, that is the treeing path, varies accordingly. Now, what is the essential requirement? What is the essential requirement for a partial breakdown measurement? You do have, you can say, PB detector. As you know, and most of the people in the world call it PD detector, but partial discharge they call it. But it is more proper to term it, exact terminology is partial breakdown or local breakdown, the breakdown which does not bridge the two electrodes where it is taking place. So the PB is a more appropriate terminology for the partial discharge, hitherto more spoken, more prevalent in the world. So I would like my students to adopt PB because that tells exactly what it is happening, what is happening there. It is a partial breakdown. It is a local breakdown taking. Actually, a breakdown is taking place within the dielectric, not just discharge. Discharge has so many meanings you have learned right at the beginning. It is a breakdown. So, what is the essential requirement when you make partial breakdown in the laboratory? You measure for partial breakdown by kind of a current pulses injected in the circuitry. And the current, because of the partial breakdown, breakdown takes place. Whenever breakdown takes place, high current flows. And in this case, the repetitive current is there because as soon as the single discharge or say single breakdown takes place, the potential drops and it takes time to build up the potential once again to the level where the breakdown can take place again. So this is a repetitive pulse of discharge current due to breakdown. And such kind of a pulse current, what would it give rise? EMI, electromagnetic interference it will give. So we do measure the electromagnetic interference when we measure the partial breakdown. Now, we are interested in measuring the partial breakdown activity within the test sample. For measurement, you require a transformer, you require a coupling capacitor, you need to connect them all, you require a measuring impedance. So all these requirements, that of the transformer, of the coupling capacitor, this is the transformer as you can see here, and this is the coupling capacitor as I mentioned. And these two are part of the circuitry we have learned. We'll learn it once again. And they are connected with the help of not just simple wire, but with the help of a pipe connection is there. Why pipe connection? When you increase the dimension of the conductor, the field intensity goes down, and that would require very high voltage for the partial breakdown around the conductor to take place. If you had taken instead of this pipe a single wire, you could have done the measurement. But around the single wire at certain voltages, there would have been partial breakdown activity, corona activity in the circuitry. And that is what you don't want. Nowhere in the whole circuit or measurement circuit, partial breakdown activity should take place except in the test object what you are measuring. So the whole circuitry, whole connections, everything is designed in such a way, large electrode system, stress control, the method of stress control, as you see on the top of the transformer here, such a dome-like stress control. This is the ground electrode also, a big electrode is given on the top of the coupling capacitor, also a dome-like electrode has been given shape, Then you are making the connections with pipe, and this flexible pipe like electrode is coming to the test object. This is the test object as you see it here. Hmm? So all connections should be free of any kind of partial breakdown up to the voltage you want to make the measurements. So this photograph, a PB free 100 kV transformer, a partial breakdown free 100 kV transformer, and 1.1 nanofarad. This is a capacitor, as you see it here. This is a capacitor, not behind this insulator. About you see it here is a capacitor. 1.1 nanofarad. This is also a standard capacitor, and it is designed in such a way that it has very low losses. It is not made out of gas or vacuum, but it is made of oil and solid dielectrics, but it incurs very low uh, real power loss. This is the coupling capacitor. A coupling capacitor, you can have this, but in case of standard capacitor, uh, it should be loss free. Yeah. So this is a photograph of a PB measurement circuit as installed in high voltage laboratory way back in uh, 1983, and it is working very well. This special kind of transformer at that time, and you see the body of the transformer is not metallic. The body of the transformer is fiberglass reinforced plastic to make this transformer to be uh, partial breakdown free up to the rated voltage. And we have tested this 100 kV transformer is PB free up to 95 kV. So this is, now we'll go to the circuitry. Yeah, as you can see here, there these are if these are the three possibilities of the connection. So this was the high voltage transformer as we saw, and this is the high voltage coupling capacitor CC. In between are the connections, and this is the test object. This is the test object, and this is measuring impedance, and this is the PB detector. As I mentioned just now in the circuitry, and this is a capacitive voltage divider. As you see here, this is a capacitive voltage divider for the measurement of voltage applied on the test object. And this here RS is a series resistor, also PB free series, a resistance put in the circuit in series. Can you imagine what is the purpose of this series resistance? It is to limit the current going to the test object in case a short circuit, in case a failure in the dielectric, because the partial breakdown measurement is again like in the capacitance formed by the dielectric. So in case dielectric fails during the measurement, the no excessive current should be drawn from the test transformers, because these test transformers are designed for very, very low current. This particular one is for 1 ampere. So to limit the short circuit current, series resistance, it can be done there. And when you connect the whole circuit, as you can see it here, these three circuits, I'll describe what are the advantage and disadvantage, what are the rather choice, what should be the choice under different conditions. for these circuitries. You can measure with all these three connections, as you can see more in detail in the book or on this PPT. But as soon as you connect the whole circuitry, before energizing, you put on the partial breakdown detector, and you have to calibrate the pulse at the detector for certain intensity of discharge current. When the, as I said, partial breakdown, that is a loss of insulating property locally, and every time the breakdown, local breakdown takes place in the dielectric, any dielectric, there will be a current pulse current flowing in the circuit or through the dielectric, and that pulse current repetitive gives a certain magnitude. According to the magnitude of the current, it gives a you can say it can be identified on the PD detector oscilloscope, and the height of the pulse should be calibrated. So this is a standard kind of a standard a capacitor. Uh, yeah, just a minute. Yeah, yeah. This is a standard capacitor which is charged and generates pulse of specific uh, charge, and that is applied across the test object, and the uh, the pulse is recorded at the PD detector for different value of discharge current, and that gives you an idea about the magnitude of uh, discharge current, and that actually also determines the sensitivity of the whole detection. What should be the sensitivity? What sensitivity means? What is the minimum value of discharge which can be identified, which can be recorded by the PD or PB detector? That is the sensitivity. Minimum value of discharge current in the breakdown, which can be identified, which can be located by the detector. So you give here pulse of different magnitudes of for calibration, different magnitudes of discharge in picocoulomb, and then you try to identify on the PB detector, and that is how you can say that is partial breakdown of what intensity, what discharge in coulomb is being is happening in the dielectric, in the test object. Yeah, the calibration, as I mentioned, is done with standard calibrating charge generator. This what we have made. This is standard calibrating charge generator. Such equipment is available. This is a you can say standard capacitor giving charge of specific value across any circuit. So that is put across the test circuit, and PD detector is made to detect that, and then you can say what is the sensitivity. You can set the sensitivity of the PD detector. Yeah, the This is the discharge or the charge injected in the circuit due to local breakdown or partial breakdown. The magnitude of charge we have learned earlier is QA. A stands for apparent charge. You have to go back to the description what we did in a number of lectures back. The apparent charge can be set in such a way that which can be detected by your detector to the order of less than 1 picocoulomb, less than 1.0 picocoulomb. It can be set in such a way that the PV detector can be set in such a way that it is able to detect a charge injected in the circuit because of when we apply the voltage, it will be because of the application of the voltage or the field intensity, but calibrated with the help of this standard calibrating charge generator. And so that is how the sensitivity of the circuit is fixed. Yeah. Then yeah, the A circuit in figure A, in order to protect the measuring impedance Zm and the voltage measuring unit from the over voltages developed at breakdown, we provide we choose the connection in this way. Circuit A is chosen to in case you may anticipate or may think that a breakdown while measurement may occur. It is possible. One can know beforehand that you want to measure at certain voltage and you have never measured at certain voltage. When you increase the voltage, there is a possibility of breakdown occurring in the test object. In that condition, the measurement is done in such a way that to protect the measuring impedance Zm and the voltage measuring unit from the over voltage developed at the breakdown. You choose the circuit A. Yeah, I'll have to go to next slide. You see that is when you are, that means in A circuit you are measuring from the low voltage electrode of the coupling capacitor, as you can see here, from the low voltage electrode of the coupling capacitor. In circuit B connection, you are measuring directly at the low voltage electrode of the test object. You are measuring in B directly from the low voltage electrode of the test object. Low voltage arm of the electrode formed by the dielectric. Capacitor formed by the dielectric. You measure, and in the third, you are measuring double from both the sides, as you can see from the low voltage electrodes of the test object as well as the low voltage electrode of the coupling capacitor. Both you are measuring a circuitry which is utilizing both of them. Yeah, one thing I think I forgot is that what is the role of coupling capacitor? If the far end of the circuit is kept to be at open circuit. Nothing is terminating the far end where we have put the coupling capacitor, as you see here, where we have put the coupling capacitor. There may be reflections there of the pulses produced in the test object, the partial breakdown pulses produced in the test objects, and this reflection may interfere the actual measurement of the pulses produced. So you must terminate the far end of the circuit with the help of a coupling capacitor. As I mentioned in our laboratory, it is 1.1 nanofarad coupling capacitor. So that is also a requirement for the circuitry, the partial breakdown measurement circuitry. And as you see here, if we just read here, you will just a minute. Yeah, try to read. I'll come to it. Yeah. Now, if the capacitance of the coupling capacitor CC is smaller than the capacitance of the test object, the sensitivity of the measurement with circuit as shown in B is higher than with the circuit discussed with the measurement at coupling capacitor. That means A. In case the capacitance of the coupling capacitor is smaller than the capacitance formed by the test object, the sensitivity of the measurement with circuit shown in B, the B circuit, is higher than the circuit discussed with in circuit A. That means what? If the capacitance of the coupling capacitor is smaller, that means the capacitance of the test object is high. The sensitivity of the measurement with circuit B is better. That means higher capacitance test objects, for higher capacitance test objects, the sensitivity is higher for the circuit B. As we can see, the circuit B is more suitable for this circuit B is more suitable for higher capacitance test objects. That means we are not actually dividing the capacitance here. We are measuring over the high capacitance test object. And the bridge circuit shown in 3, the bridge circuit, which is when you are measuring the PB from both the sides, the bridge circuit shown in C is more suitable for the measurement at sites having high electromagnetic interference. What I'm talking about, EMI, external EMI. Even the radio signals, your communication signals, radio signals interfere the measurement, because this measurement is very, very highly sensitive measurement. So people in those areas where a lot of external EMI, electromagnetic interference, prevails, people may have to wait for that to go, or make a Faraday cage, so that when you in the measuring part, in the whole measurement, you do not you suppress. Faraday cage would ground the external EMI or external signals, so that you can make the measurement without disturbance from externally generated electromagnetic interference. So for that, The bridge circuit C is more suitable for the measurement at sites where such kind of a provision, Faraday cage, and etc., cannot be made, and or where lot of electromagnetic interference from external sources prevail. Sometimes it is difficult to make distinction between the PV pulse generated within the test object, that is what you are interested in, and the external interference. So they look like to be the same, but you can find it out. How can you find it out? I've been doing it. You reduce the voltage applied, and the pulse are still being shown on the detector. That means it is from external source. Nowadays, however, incorporation of suitable filters, I mean, the PV detectors have been developed in such a way that they can distinguish the pulse from external source and the pulse from internal source or the internal circuitry. So the PV detectors have been equipped with suitable filters, so that in the modern PV detectors, which facilitate the measurement even under external EMI. This is the sophistication in the measuring technology and in the PV detectors these days, so that you need not make a Faraday cage, etc. Earlier days, Faraday cage was also being used. So with the help of filters, the detector is able to detect the external source EMI and filters it, and only the EMI, as I said, the pulses produced within the test object, which also are kind of an EMI, are detected by the PV detector. So calibration of the measuring circuit is required to be done with standard calibrating charge generator, as we have discussed, and the measurable quantity of the apparent charge and the sensitivity of the measurement depend largely upon the calibration. So this is what we have already discussed, and you should be, I hope I have made my points clear. And of course, if not clear, we should read. I would say we should read from the books. Yeah, we are coming towards the end of this lecture. The high voltage uh, tests, I mean, testing of selective electrical apparatus is also done. I mean, every apparatus, when you do the testing or the measurement of different parameters of the quality of its dielectric, requires slightly different techniques in connection and in detection, etc. The power frequency spark over test is done on the surge arresters. You know, the surge arresters or the lightning arresters uh, give a kind of a spark over for a pulse of above certain magnitude. And this is a kind of a routine test, the spark over test for the with the impulse voltage for the surge arresters, because surge arresters, as you know, work for, people call it high frequency surge. It's not high frequency, it's a single pulse of very fast pulse, fast rise and slow decay. So it works on pulse voltage, that it grounds the pulse voltage. The job of the spark surge arrestor is to ground the pulse voltage, spark over to take place across a, by that spark over may be by lightning or switching surge of desired shape. The arresters The arrestor has to withstand at least 1.5 times the rated voltage of the rated value of the voltage for 5 successive applications. That is what the test of the surge arrestors is, that it is tested uh, 1.5 times the rated value of the voltage for 5 successive applications. When the pulses are applied, not just single pulse, number of pulses are applied. In this case, 5 pulses must be applied repeatedly, consecutive. So, and it must be this time. Yeah, this may be required to be done under other than the simple dry condition of weather. Impulse spark over tests. These tests are conducted on some samples used for power frequency spark over test. These tests made to ensure that arrestor operates successfully each time for a standard impulse of a specified voltage. So that is, uh, I, you must ensure that it must make a spark over above a certain magnitude of the pulse. So that is also impulse spark over test are done. Then uh, on the surge arresters, then the front of wave spark over test. These tests are conducted to make surge to make sure that the flashover occurs for every steep rising waveform of high peak value when applied on surge arresters. This test is performed with impulse having a rate of rise of 100 kV per microsecond. In 1 microsecond, when the pulse rises to the tune of 100 kV, it's a very, very fast uh, wavefront pulse. So these tests are conducted to make a make sure that the flashover occurs for every steep rising wave front. Why? To ensure it is possible that the steep rising wavefront pulse may not lead to a flashover. So to ensure that for every steep rising pulse, the flashover occurs for the surge arresters, this test is also performed. And for that, what will you have to do? Uh, I mean, if it doesn't if it doesn't make a flashover at the specified voltage, you may have to increase the specified voltage, which then it is not meeting the requirement. So you may have to reduce the gap distance so that the flashover occurs. You may the surge arrestor design may not be satisfactory. You may have to make changes if flashover does not occur for the steep rising wavefront pulses. And these are very typical requirements for surge arresters. So these are relevant for impulse voltage, mainly lightning impulse voltage, magnitude of pulse, shape, etc. must be, and these are done according to the specifications, as I've been talking about, the number of pulses, the magnitude of the pulse, etc. for the specified rated voltage surge arrestor. These are done according to the specifications. Yeah, when we come to the high voltage test in power cables, we have mention that in the power cables, not only at the finished stage, but also in the intermediate stage, high voltage tests are performed to ensure the insulation quality. And since there's a lot of insulation involved in power cables, it forms very high capacitance, and for that, the suitable uh, uh, equipment for uh, testing high voltage power cables is is the resonant uh, test voltage generator. That means where the inductance of desired value can be uh, uh, taken into circuitry, which takes place automatically. The inductive reactance uh, is adjusted automatically by variable inductors are used, or we vary the frequency to make the inductive reactance and the capacitive reactance as close as possible, or under the resonant conditions when you supply only uh, the real power. Yeah, the certain tests for continuity of the conductor, routine tests, as I mentioned, during the manufacture. Then 2.5 times so U naught is applied for 10 minutes in power cables, and uh, the DC tests are performed on power cables at site. When after laying the power cables, DC tests are performed as a in general on any equipment after installation, after laying the cable, after installation of the transformer at site is always performed with DC, and that may require higher voltage than the AC magnitude, and also longer duration of the voltage is applied in case of DC. And these are all once again specified by the uh, various specifications you may one day required to follow in the high voltage laboratory if you work there. So this, with this, we come to the end of measurement chapter. The quality, the condition, and mm, uh, quality and condition mainly of the dielectric or the finish of the dielectric on an equipment. These were the parameters which can provide you the an idea about the quality of finish of the dielectric. And for all these measurements, standard values are recommended in various specifications. So one must always uh, read the specifications. But method of measurement I have tried to describe here. That is simple high voltage tests of AC, DC, impulse voltage, measurement of partial breakdown, very important, measurement of tan delta, insulation resistance, as we discussed by different uh, uh, apparatus. So all these reveal the quality of the dielectric, and you ensure the quality to get the desired length of satisfactory service of the apparatus. So international electrotechnical commission standards are nowadays being followed in India also very widely. uh, we used to have our own BIS, Bureau of Indian Standards, but nowadays many of the specifications for certain conditions of measurement are we are following IEC in our country. That's not a bad trend, I would say. Uh, so with this, I would make a break. Uh, and let's call it the measurement chapter 9 is completed. In the next chapter, I'll introduce you with the how a high voltage laboratory is laid. I mean, when you want to plan to make a high voltage laboratory, what should you have in mind? So we will, in maybe in our last lecture, we'll talk about that. Okay.